My name is Yuafi Prince Owusu, and today I will be presenting on memory cache mapping techniques, exploring the fundamental techniques that bridge the speed gap between the CPU and the main memory, defining how data blocks are mapped to cache lines to improve processor access speed. So when we say cache memory is a small high-speed memory located close to the CPU. It stores frequently accessed data and instructions to bridge the speed gap between the fast CPU and slower main memory. This reduces latency and improves system performance by exploiting two key principles. So importance of cache memory, we have its fast data access, its reduced latency, performance impact, locality exploitation. When you say fast data access, small high-speed memory that stores frequently accessed data and instruction, and they reduce latency, significantly lowers average memory access time for the CPU. For the performance impact, cache hit versus misses, data not found, and directly affects system performance. So, overview of cache mapping techniques. So, cache mapping techniques dictate how blocks of main memory are placed into cache lines. Each method offers a distinct balance. So, we have the direct mapping, the fully associative mapping, the set associative mapping. When we say the direct mapping, each main memory block has a single predetermined location in the cache. Fully associative mapping. So any main memory block can be stored in any available cache line. And third, the set associative mapping, a hybrid approach where blocks map to a specific set of cache lines within which they can be placed anywhere. So I'm moving to the next line. We have the direct mapping. So in direct mapping, each block of main memory maps to a specific unique cache line determined by a simple modular operation mouse to cache line, and this simplicity translates to simple hardware design, lower implementation costs, fast access time due to direct calculation of cache location, prone to high conflict misses if frequently accessed blocks map to the same cache line. So no complex replacement algorithm is needed as new data simplify overwrite old data in the assigned line. So I'll be moving to the next line. So we have the fully associative mapping. For the fully associative mapping, it provides maximum flexibility by allowing any main memory block to be stored in any available cache line. This approach significantly reduces conflict misses, leading to a higher hit rate. However, it comes with specific trade-off. So it requires setting all cache tags simultaneously, which demands complex associative search hardware. And it has higher hardware costs and slower tag comparison due to complexity. It employs sophisticated replacement algorithm like least recently used as the LRU to manage cache lines. Then we have the set associative mapping. For the set associative mapping, it strikes a balance between direct and fully associative approach. This cache is divided into a number of sets, and a main memory block maps to a specific set. Within that set, the block can be placed in any of the available lines. So we have the balance benefit, the moderate complexity, set-specific policies. Combines the speed benefit of direct mapping with the flexibility of associative mapping. reducing conflict misses, and the moderate complexity involves a moderate level of hardware complexity compared to other methods. And for the separate specific policy, replacement policies are applied only within each individual set, simplifying management. Moving to the next slide. So comparison of the techniques. So you have the technique, the simplicity, the flexibility, and the key characteristics. So under the technique, we have the direct mapping, the fully associative, and the set associative. And for the simplicity, we have highest simplicity, lowest scores, and lowest simplicity, highest scores, moderate simplicity, moderate course, based on the technique, the direct mapping, the fully associative, and the set associative. So for the flexibility, we have lowest flexibility, highest flexibility, and balanced flexibility. So the key characteristics. First, one-to-one mapping. Any block can go anywhere. Block maps to a set. Flexibility witnesses. So the optimal choice of cache mapping technique depends heavily on the specific requirements for cache size, design speed, and budget constraints of the system. So in summary, understanding cache mapping techniques is crucial for designing and optimizing modern computing systems. The choice among direct, fully associative, and set associative mapping involves strategic trade-off between hardware complexity, cost, and the crucial cache hit rate. So when we come to the crucial for performance, we know that the cache mapping is fundamental for efficient CPU memory interaction, significantly impacting system speed. And when it comes to the balance trade-off, the decision involves weighing hardware complexity against design cache hit rate and system cost. And under the three core techniques, direct, fully associative, and set associative method, each offer unique advantages. And under the designing optimized system, in-depth knowledge of these techniques empowers the design of highly efficient cache system. So I hope based on my explanation, you understand how cache memories works. Thank you.